to the 2026 Weyl lectures. Weyl and Morse lectures are our main yearly lectures where we bring world leaders to expose recent developments that are shaping a field. Our speaker this year is Maryanthe Malliaris. Is that pronounced correctly? I hope so. From the University of Chicago. He has made decisive contributions to model theory and especially its applications to related areas. These include her work on the stability and complexity of model theory and its connections to combinatorics around Szemerédi's regularity lemma, as well as to set theory. And these have led her to the solutions of a number of long-standing problems. Together with Shelah, she resolved the question of the cardinals P and T from topology being, I think, unexpectedly equal. I think in that area, after Cohen's forcing, mostly people would have expected things to be undecidable. But this is a sign of some kind of structure when you can actually show it is decidable within the axioms. By the way, it was 63 years ago, in 1963, that Paul Cohen gave his lecture at the Institute here, showing that the continuum hypothesis is undecidable. I think that was the very first place where actually people started to believe him, because Cohen said it was correct before. I think they did not believe him, or at least so he told them. Anyway, we'll hear more about this, as well as the connections of her work to complexity theory, learning theory, and even differential privacy lectures. Maryanthe has won numerous prizes and awards, including the Hausdorff Medal. The title of a lecture series, starting this one, is Learning from Complexity. Okay.
Okay, so thanks everybody for coming. This is a wonderful occasion, wonderful to be back here and remember a couple of very productive terms I spent here, many wonderful mathematical conversations and theorems, some of which will feature in these lectures. So great to see many colleagues and friends. Thank you for coming. Okay, so I'll speak about learning from complexity. And so this will be a series of 3 lectures. I'm going to talk about some recent developments in model theory and sit down. Some recent developments in model theory and various interactions. So this lecture will be a sort of gentle introduction to some of the themes I'm going to talk about. All right, so learning from complexity. So I want to start with the theorem. So this is, I'm giving a very specialized version of a theorem of Simon Shelah from 1972. So in this very specialized version, I'm stating it only for graphs. I'm stating it only for the cardinal out of 0. So in this version, it's also a theorem of Erdős and Mackay. Okay, but let's write down the theorem and then we'll talk about it. So theorem. So specialized version of Shelah 72, Erdős, Mackay. Okay, so we will see more of this theorem in due course. So suppose we have a graph G. This will be an infinite graph. So if the graph G contains a countable set of vertices, over which it realizes uncountably many partitions. I'll write this down and then I'll explain. Over which G realizes uncountably many partitions. So here there are 2 sizes. There's small and large. Uncountably many partitions. Then G contains an infinite half-graph. Okay, so we're asking some questions about this. Let me explain what everything means. So we have a graph G, we have a set, let's call it A. This is our countable set. Every other vertex partitions it into 2 pieces. And the intersection with its neighborhood, the ones it's connected to, the ones it's not connected to. And the question is, as you vary the other vertices, how many different partitions of A do you get? you get uncountably many, even though this was just a countable set. So that's the counting side. Is there a countable set over which there are these many partitions? What's the half-graph side? So a half-graph is you have infinitely many A's and infinitely many D's, and there's an edge between AI and DJ, if and only if I is less than J. And let me say that for me, half-graphs are always bi-induced, so I care that between an AI and a BJ, there's an edge if they go in this direction, there's a non-edge if they go in this direction, and I have no opinion on how the A's and the B's are connected to each other. Okay, so the question for you is, why should this be regarded as a theorem of model theory rather than, say, a theorem of combinatorics? So it's telling you that from a certain count, you get a certain configuration. And so I want to suggest that a reason we can think about it as a theorem of model theory is that model theory gives you the point of view to see this as a characterization, right? Right now, it's not a characterization. So if you have these many partitions, then you have a half graph somewhere, but you could have a graph with an infinite half graph, for example, the half graph indexed by natural numbers, where you don't have any phenomenon like this. So one aspect of the model theoretic point of view is going to be to say, look at the elementary class of graphs. So rather than just looking at our graph G, this infinite graph G, we'll look at the class of all other graphs that satisfy the same sentences first order logic in the language of graphs. And the claim is that in that case, you really do give an if and only if. You have some graphs in the class where you have these very expressive pieces, these small sets over which you have many partitions, if and only if you have other graphs in the class where you have half graphs. So before writing down a theorem, let me just explain to you how this might look, for example, in the case of the natural numbers, in the case of just these half graphs. So rather than drawing a half graph, maybe it's a little bit easier if I explain elementary classes with linear orders. So for this example, I'm going to draw linear orders and talk about cuts. So what's the elementary class of the natural numbers considered as a linear order? So this is a set, we have a linear order on it. The theory says this is a discrete linear order with the first element and no last element. So also in the class will be, so we have a copy of the natural numbers, we have a copy of natural numbers followed by a copy of Z, followed by 2 copies of Z, have natural numbers followed by a copy of R, where every point is replaced by a copy of Z. And in that element of the elementary class, you do have a countable set in which you have lots and lots of partitions. Okay, so let's write down a theorem.
Yes, I don't think.
Yes.
Yeah, I didn't understand these arrows, what they are.
Okay, so let's say, all right, so this arrow is the natural numbers as an ordered set. Okay, so here's, okay, and it satisfies T, which, so what are the axioms here in the language of linear order? It says this is a linear order. So this relation is a total linear order. There's a first element. There's no last element. Every element has a unique successor. Every element of one has a unique predecessor. Okay, so that's the set of axioms. Now, there are other models in this theory. There are other linear orders that satisfy this. For example, let's say I take a copy of N followed by a copy of Z. So let me tell you how to make this into a linear order. If I have 2 points from here, they have the usual order on N, 2 points here, you have the usual order on Z, and a point here and a point here, the N goes first. That's a total order. It's still the case that every element has a unique predecessor. Every element but one has unique predecessor. Every element has a unique successor. There's one first element, there's no last element. So this is somebody else in the class. I could have another copy of Z, that's somebody else in the class. I could have another copy of Z, but I could have more complicated structures. They don't just necessarily, they'll be linearly ordered, but imagine that I have a copy of N, I'll draw it as a point, well, maybe I'll draw N, and then I take a copy of the rationals and I replace every point by a copy of Z. So that's still a linearly ordered set. It's still discrete, but I've kind of built this density into it. So now if I take take the 1 point off of every one of the chains, representing one of the rationals, I have this countable set, and now I have lots and lots and lots of cuts. So, okay. So notice that if we want to stay within the elementary class, I mean, this is a good question, because in order to see, right, this is something that really needs density. And if you just have an infinite half graph, you don't really have anything like density. You don't have very many cuts over natural numbers. But, if you look at other models within the class, first order logic can only tell you things about the linear order being discrete, in the sense that from the point of view of any element, there's one before and one behind. It doesn't tell you something about, how densely the copies of Z are arranged. Yes.
Is it the claim that those various structures are elementary the equivalent?
Yes. Yep, exactly. More questions? Yes.
So what if I wanted to add an axiom, like where every two elements, there's only finitely many things between them?
Okay.
Why is that not one of your axioms?
Good question, because that doesn't take that. You can't do that with a single axiom. So you can write down a single axiom that says there exist two elements. You can say that there are two elements with distance 2. So maybe let's say a little bit differently. So we can define this element, which is the first element. We can say there's somebody that has, there exists X with only one element before it, right? There's somebody with only 2 elements before it. There's somebody with only 3 elements before it. There's somebody with only 4 elements before it. These are each different axioms. We can't write down a single axiom saying there's only finitely many elements before me. So actually, you can turn this around and see something about what elementary classes you're doing. So you could write down a list of axioms or a list of formulas. So phi n of x says there are at least elements below x. And suppose you write down this phi n of x.
Right a bit bigger.
All right, so maybe since this is just an example, I'll just say this here. I could write down a set of formulas. So this says there's at least one element before me. There's at least 2 elements before me. There's at least 3 elements before me. There's at least 4 elements before me. This is a collection of formulas. There are countably many of them. In this structure, there's nobody that satisfies all of these, right? But every finite piece of it is realized by somebody. So one of the things that we'll see in the course of this talk, right, anytime you have a collection of statements like that, you're describing something which is finitely approximated, but doesn't necessarily exist there. There will be somebody else in the elementary class, somebody else elementarily equivalent to what you started with, where such an element exists. And so that's one of the engines where you can start to see anytime you look at a structure, right, you have a question of what's finitely approximated there, right? And that's part of what the elementary perspective allows you to see. Great, more questions.
What is elementarily equivalent?
Elementarily equivalent means same set of sentences of first order logic. I'm not sure where the word elementary comes from. This is a, yes. And it's, so M elementarily equivalent to N, so it's written like this. Great, okay, so my claim is that the model theoretic, one initial aspect of the model theoretic point of view is you look at a particular structure, but rather than considering it in isolation, you look at the class of all other structures that satisfy the same set of sentences of first order logic, the elementary class. And looking in that class, you start to see interesting if and only ifs about phenomena that all happen together or all happen separately. Okay, so let me write down the theorem. Well, again, a special case, but let me say something about, so some special cases of Gauss unstable formula theorem. So this is from classification theory, 1978. Okay, so this is to explain exactly how this becomes an if and only if in the case of graphs. All right, so for an elementary class of infinite graphs, I will write for infinite graphs. Let's call it gamma and edge relation R, the following are equivalent. So one, this condition up here, some graph in the class has a countable set over which It realizes uncountably many partitions. And so, and this is telling us that the graph edge relation is aleph 0 unstable. So aleph 0 is countable, right? So you're saying unstable of this size. There's a set of this size over which there are many partitions, many types, we'll say in due course, to some G in our class as an infinite half graph. So again, by induced, I just mean that there's a collection of A's and a collection of B's with AI connected to BJ if and only phi is less than J. In fact, this arrow we've seen we can do in the same graph. 3 some G and gamma has a set of lambda vertices. So here, lambda is any infinite cardinal. We have a set of lambda vertices over which we have at least strictly more than lambda partitions realized. Partitions. And this gets called lambda unstable. Okay, so you can do this for any infinite size. For any linear order.
Sorry, that 3 is there exists an infinite lambda or?
For every, it's for every, well, it's either one will be true, but yes. So you can have a different condition for every infinite lambda, but if you can do it for one, you can do it for every. So there's an important disclaimer here I should make for people who thought about stability. Here I'm describing to you stability for formulas. And there's an interesting question about stability for theories when you ask about all formulas in the language. I'll say a little bit about that reduction, but this is really about a particular formula. So if in some size you see that there's great expressivity, then that will happen at every infinite size. Any infinite linear order I, some G contains I index half graph. So you could have half graphs indexed by whatever you like. They could be indexed by the rationals, they could be indexed by omega, they could be indexed by reverse omega. Questions about what I'm saying here so far? Yes.
Elementary class, you mean a class under the elementary rules?
Yes, I mean, I'm looking in the language of graphs and I look at all other, I start with my infinite graph G and I look at everybody else that satisfies the same set of sentences of first order logic in the language of graphs. Of course, this theorem works in generality. You take a complete theory and you take a formula. And so this is talking about the set of models of that complete theory when you're asking about instability for the formula.
And then the second, what's the, you say by induces?
Oh, by induced. So I'm just pointing out that when I say there's a half graph, I'm not saying it's a subgraph and I'm not saying it's an induced subgraph. What I'm really saying is if you give me an AI on one side and a BJ on the other side, there has to be an edge if J is greater than I. There has to be a non-edge if J is less than or equal to I. But I have no opinion about edges here and no opinion about edges there.
But the A's and the B's have to be
Two disjoint infinite sets. And in this notation, I can, so maybe when you have AI, I and I, and BJ, J and I, so you give me some linearly ordered set, you have two infinite disjoint sets indexed by that linear order, and then you just have this asymmetry between.
It is joint. I thought you wanted also the case where they're the same. Your first.
Oh, okay. So in the first case, so I was making a slight translation here because it's a little bit easier to talk about the elementary class of a linear order than it is to talk about half graphs. So you could, if you want to make this look exactly like a half graph for this, this is your formula for the xy, is the formula x is less than y, then here you are. So you could take, your x's is the evens, and your y's is the odds, and then phi holds between I and bj if and only if I is less than j. There's no problem if they come from the same set, but let's have them actually be different elements. Is that
I understand they can be different, but do you require that they're disjoint or just any two sets angry?
We might as well, okay. It's not really important because the moment you have arbitrarily large linear orders, it's easy to separate but into evens and odds. But we could, yes, at this level of generality, you could take, I'll take them to be separate. But it's, yes, there are certainly many other ways you could do this. Okay, and then the last one is for arbitrarily large finite K, some element of the class as half graph size or length K. Okay, so the point here I want to make is that all of these, all of these different conditions for arbitrarily large finite sets, you have this expressivity, you have these arbitrarily long half graphs indexed by any linear order you like. One of the equivalent conditions is whether you have arbitrarily large finite half graphs. So in the unstable formula side of it, okay, so there are many other conditions of the unstable formula theorem that we will discuss in due course, but in the unstable side of it, in every infinite size, you have this expressivity somewhere, and you have arbitrarily large half graphs, in particular arbitrarily large finite ones. But in the stable side of it, where you have the good behavior over every infinite set, you can't really see more than the size of that set. You have a uniform finite bound in the size of the half graph. Okay, so okay, and again, this is something you see looking at the elementary class. So if we look at this collection of things, notice that half graphs are something you can easily see in the finite. But if this is giving us a count on one side and a configuration on the other, half graphs, you can talk about having A1 up to AN, B1 up to BN, AI is connected to BJ if and only if I is less than J. But the counting isn't something that you could at all obviously see in the finite. In fact, you can't, right? So let's give an example of a graph. So here's a matching. So we have the AIs up here and the BJs down there, and every AI is connected to exactly one BJ. And let's compare this to half graph, which is, we have the same AIs up here, the same BJs down here, and they're connected forward. So let's ask, if we look at the B's in both cases, how many different partitions do we realize over the B's? Now, the actual partitions we realize are different. So in this graph, we can get all of the singletons, and if our graph is bigger than the set we've chosen, we can also get the empty set. Down here, we can get the co-initial segments. So we get different ones, but the number is essentially the same. So in a finite graph, we'll say in a moment, you would expect to see a division at BC dimension, or finite infinite BC dimension, but you don't see the division at stability. This is somehow finer. So it's interesting. This finite combinatorial object is something you see with a count, but it's only a count you see once you go to the infinite. So in fact, okay, so we could try count. So you could write down, for example, K of, maybe you have a class, an elementary class of graphs, you have the edge relation, and you have some lambda, which would be a finite or infinite cardinal. And let's say this is the maximum number of partitions we see over some set of size lambda in some graph in the class. Now, what happens when lambda is finite? So you have the Sauer-Shellock-Perlis lemma that tells you get a polynomial exponential dichotomy for BC dimension. So you have polynomial exponential. So we can write Sauer-Shellock-Perlis. All right, but as we've seen, the half graphs really don't stand out in the sense of counting. When lambda is infinite, you still have the polynomial exponential. So BC dimension has, from the beginning, there was this model theoretic interpretation and interaction.
Can you explicate that a bit? What this VC dimension is and what's polynomial?
Sure. Okay. So let's go over here. So here's our picture. These are all graphs. All right. This is the picture we're aiming for. Within the class of all graphs, we have those of bounded BC dimension, and within those we have stable. Okay, so what is VC dimension? So anytime you're in a graph, so now that picture was the class of all graphs, and this circle is a graph. Okay, so here we have a graph G, and here we have a set of vertices. So say this set is shattered if we look at any other vertex in the graph and induces a partition, the ones it's connected to and the ones it's not connected to. Do we get all possible subsets? So if there's a set of size n where we get all possible subsets, say that the graph shatters a set of size n. So the VC dimension is asking how large of a shattered set do you have? So the polynomial exponential dichotomy is telling you if you're trying to count partitions, you'll get something like, so if n is the size of the graph and d is the largest size of the set you shatter, you'll get something like n to the d if there's a bound in the size of the shattered set. Otherwise, the largest number of partitions you could get is if you somehow name all subsets of the graph. Now, this if you name all subsets of a particular finite size, so you could get something like 2 to the d. So you have to exactly say when you fall in one case or the other, and they're constants. But you essentially either get a polynomial or exponential bound. What?
To the end.
Oh, thank you. To the end. Okay, great. People are paying attention. All right. Any other comments I should make about this?
Just to be clear, when you talk about number of partitions, are you allowed? How many conditions does it impose? Like you're allowed intersections here, from what I understand. To an unbounded extent, or you're exactly what you're.
Okay, so this is a good question. So this sort of really gets to the question of, am I thinking about the types in a particular formula, or am I thinking about all formulas in the language? So here I'm really doing a particular formula. I'm just thinking about the edge relation. But indeed, it's a very interesting and important question to think about all types. Maybe since you mentioned that, I'll just say as an aside, which is very much worth mentioning. So in this theorem, you're either stable everywhere or nowhere, and that's because you're looking at a particular formula. But if you were trying to count types using all formulas in the language, so aside stability for theories, so you could say T is lambda stable, a theory, an elementary class is lambda unstable. So you could ask, this will just be an aside for a moment. You could ask the question, in a model of the theory over a set of size lambda, do you always get lambda types or do you get more types? And by definition, you're either stable or unstable at a particular size. What happens is lambda varies. It turns out if you're lambda unstable somewhere, you're lambda unstable everywhere. But if you're lambda stable somewhere, so T is unstable, so this is a theorem also of Shelah classification theory. T is unstable if it's lambda unstable in all lambda, but it's lambda stable. It's stable without a lambda if it's lambda stable in all lambda with the property that lambda is lambda to the power of t. So the power of t is just the size, right? It's a calculable theory, right? The lambda is the alpha is lambda. So, but what?
Can you explain that?
Yes. Okay. So, all right. So you're saying you look at all possible cardinals, and if you see if you see somewhere that you have too many types, so as an aside, this is where you're using all possible formulas in the language. So this is a more complicated statement than the statement here where you're just using the graph edge relation.
So the first statement that you wrote over there looks a lot like the equivalence between 3 and something.
Yes. So when we're in a graph, here we're picking a particular formula. This is the edge. But there are lots of other formulas. There's a fixed finite Boolean combination of edges. There's, maybe you're in a graph that has also a field structure on it. So you have different formulas coming to the field structure. Maybe you also have a linear order.
The formulas are what gives us the partition? Or?
Yes. Okay. So you could look slice-wise for each individual formula, and you could ask how many partitions do you get in that slice for that particular formula, and then you have this. But if you want to talk about theory, you look at all formulas at once. This is something now that really only belongs to the infinite world. You look at all formulas at once and you ask, okay, so how many, maybe a different way of saying partitions is you have some set here, you have an element here. For every possible formula in your language with parameters from A, this element either satisfies it or not. So you look at, you can describe that element with all the formulas it satisfies. This is something I'll introduce. It's called a type. It's a description of that element. So how many different types do you have using everything you can possibly say to express? So it's composed of what you see with all these different slices. But could it be that each particular slice, you know what's going on, but somehow the slices all, if you're trying to count and you're looking at all of the slices together, maybe you might see something a little bit different. So what this theorem is saying, okay, so the point is that if you try to count the types looking at all possible formulas together, it could be that you're in a particular size and you see that you have too many, but the reason you have too many is something specific about that cardinal. So cardinals where this is not the case could give you a false positive. So this is saying if, I don't know if you can see. Yes, okay, so T is the size of T. So for example, if the language is countable, let's say it's countable. Okay, so what are some examples of, what does it mean that, so lambda to the power of T, for example, if T is countable, then 2 to the aleph naught will have the property 2 to the aleph naught times 2 to the aleph naught to the aleph naught is 2 to the aleph naught. So this is a cardinal that will not give you a false positive. So if you look at this size and you don't have too many types, then for sure you're okay. And so actually the reason, okay, so the point is a theory T is either stable or unstable, and unstable means you're unstable everywhere. Stable means you're stable in every cardinal that doesn't give you a false positive. And the point is that if you look at one of these cardinals, this is, if you take a product of lambda many things, T times, this is what you get. So this is telling you that if you look at every type and you look at its slices and you project and every possible slice is small, and you know that lambda to the power of T is equal to lambda, then the only way the product can be big is if one of the pieces is big. So that's why these cardinals are telling you what's going on. And so this is really telling you that you're unstable if and only if there's an unstable formula. It's just, there has to be a single, right? There has to be a local reason. And that unstable formula is what's telling you what's going on, but you only see the presence of that unstable formula if you look in a size that doesn't give you a false positive. So this is actually, it's nice that I got a chance to explain this because, again, if we're thinking about stability, soon enough we'll talk about stability in the finite, and at the end of the day, maybe you get half graphs and you get definitions and you get all sorts of other things that make no mention of cardinals, but to see how stability works, you really, you use a lot of interesting properties of infinite sets to measure and to combine and to see differences in what's small and what's large. And maybe, maybe then they burn off and just afterwards you see the combinatorial properties. But cardinals had a role to play in this. Okay, all right, so this was.
Sorry, can I ask?
Yes.
Is it easy to say why the infinite half graph is special?
Oh, good question. So in some ways the whole talk will be about this, right? But a couple of things to say. So one is that it's telling you about a certain kind of asymmetry. So stable theories, think about algebraically closed fields as an example with their huge transcendent spaces. There's just a lot of symmetry there. So somehow there's this difference between symmetry and asymmetry. The thing about half graphs is you have the stable side, you have the unstable side. I've talked about linear order on the unstable side, but random graphs are also unstable. So instability isn't about linear, it's about asymmetry somehow. And half graphs, you can think about it as what random graphs and linear order have in common, perhaps. Another thing about half graphs that's special is if you think about how this theorem works, they allow you to make a characterization. Because if you have half graphs indexed by any infinite linear order, then you have one is indexed, say, by the rationals or by the reals, and then you can get lots of partitions over them, and then you get lots of types. So there's a sense in which it allows you to reproduce the many cuts without necessarily needing the linear order. You just need some kind of rigidity as exemplified by half-graph. More questions? Okay, so there are many things I want to say, so let me try to continue. Thank you for all of the good questions. Oh, so before I erase this, so I'll just say we want to count the maximum number of partitions we see over a set of this size using this edge relation. In the finite, we see BC dimension, polynomial exponential. In the infinite, we really see three things. So we see lambda, so this is stable. We see the version of polynomial is Dedekind number of lambda, the maximal number of cuts you have in a linear order with lambda many nodes. Let's call this polynomial. And you could, of course, like if you're in a large random graph, have 2 to the lambda. And this is what are called dependent theories, or NIP, not the independence property, and this is the independence property. Now, there's a very big asterisk here, which I will just mention, which is when you're counting in the infinite, you probably don't actually want to count the size. You want to count the smallest regular cardinal with the strict upper bound on the size you have. So really your count should be lambda plus den r of lambda to the lambda plus. So I haven't written that, but you see, so you see this emerge in your count. Your count goes from 2 to 3, or really from, really there's a trivial case. So you see stable, but you only see that when you look again. Okay, so let me speak a little bit more quickly. Now, one thing to say that already was noticed.
What do you mean by rigidity? Does that come?
What do I mean? What do I mean? So maybe so when you have a kind of, all right, so maybe rigidity is a very strong word, and I don't want everything associated with the word rigidity, but if you have half-graphs around, then there's a lot of good structure you see when you keep things in the right order. So, if you have something like Ramsey's theorem and you have an order in the set, maybe you say, from the point of view of this order, we have some kind of homogeneity. But if you're in a transcendent spaces in an algebraically closed field, you can move the elements around. It doesn't really matter the relations they have or don't have with each other. It doesn't depend on a particular order. So that's the sense in which there's a kind of rigidity, that if you have some kind of order around, some kind of asymmetry around, there are certain things that certain kinds of good behavior you can see only if you keep things in order, and that disappears in stability. Okay, so I had said that there's some kind of property you can see in the finite, which is this half graph. There's a count which you can see in the infinite. I want to say that something that you could do if you wanted to have some kind of finite count. It won't give you a count of types exactly, but you could try to record an inductive process that tells you something about how you try to find partitions. So let's look at again what happens in a half graph. So here are your AIs and here are your J's. Let's try to look in a half graph at how we can partition the B's. Well, maybe we have an element, let's call it a empty set, that's in the middle of the top row of A's, connected to everyone here and not to anyone there. So let's think about this as being a tree. So these are the B's it's connected to and the B's it's not connected to. Then I could take the midpoint here, and this midpoint splits this set again. It's connected to these and not connected to these. It also doesn't connect to these, but we'll ignore that for a moment. So let's write this is here. We could take a midpoint here, A0, it's connected and not connected. And now in each of these pieces, we could take elements remaining in partitions if they're non-empty. B10, B01, B00. And we could make them the leaves. B10, B01, B00. Now, what properties does this tree have? The internal nodes are indexed by binary strings of length less than 2. The leaves are indexed by binary strings of length exactly 2. And these two are connected. These two are not connected. This is connected. This is not connected. This is connected. This is not connected. So we're really saying that, okay, eta in. So the internal nodes are indexed by binary strings of length less than t. the leaves are indexed by binary strings of length exactly t, and the rule is that A eta is connected to the row if when I was standing at eta and eta is an initial segment of row with a 1, so eta connected to 1, concatenated with 1 is an initial segment of row, and there's a non-edge A eta B row if eta concatenated with 0 is less than row. And otherwise, I have no opinions. Right? There are many more edges that appear in this tree, but I have no opinion about them. So it's true that your half graph is finite if and only if your stability trees are finite, or instability trees, if you want to call them. And this is something that is hidden as a notion of rank. So this rank has a long history. You can see it in Cantor-Bendixson, you can see it in Morley, you can see it in Shelah, and Hodges. So was interested in this question of, in the unstable formula theorem, your stability trees, your rank is finite if and only if your half graphs are finite. What can we say about the finite bounds? So already at the very beginning of classification theory, certainly circa 1980, let's say it's stated in the form of a graph, if G has a half graph of length K, there is a stability tree or instability tree of height about log K. And if you have a stability tree of height L, there is a half graph of length about log L. Okay, so there's some finite relationship. These bounds are very far away from each other. We still don't know if they're tight.
This is all for finite?
This is all for finite, right? So Shelah had proved that if you're basically your stability tree is finite if and only if your half graph is finite. So Hodges was asking, is there any connection with bounds? And what he could get was about a log dependence in both directions. So yeah, this looks probably like many things, right? Littleston, right? Like many things that appear in computer science. But yes, so this was observed at the very beginning, but somehow not much, as far as I know, was done with it. I think stability was really thought about as something in the infinite world. Okay, so let me tell you a couple of things that. Okay, so stability was foundational, and many interesting things have come from it. I should say, I think the first use of stability, if I understand correctly, was in row bottom, Morley. So Shelah classification theory then develops a lot. And here's an example of a structural consequence of stability in the infinite, which is again in classification theory. So if you think about the example of algebraic closed fields of fixed characteristic, and the countable, your transcendence degree could be 0, it could be finite, it could be countable. But the moment your algebraically closed field becomes uncountable, you have this huge transcendence basis, the same size as the field, right? This huge set of elements that all look alike, of linear size, you might say, right? So the point is, that's an example of a stable theory. And in general, in large models of stable theories, you have phenomena like that. You have this huge set of elements that all look alike, which actually in some deep sense control the structure of what's going on, at least control the saturation. So let me state, okay, so theorem stated for graphs, I'll state it for theories. So for theories, it says if you have a complete theory and you have lambda, and you're stable in lambda, then anytime you take a model and you have a set A of size lambda and a set B of size lambda plus, there's a subset of B also of size lambda plus, which is indiscernible over A. But for graphs, we could say if the edge relation R is stable, and we have G size lambda plus, there is a subset of G of linear size, we might say, right, also size lambda plus, so two things are true. It's either a clique or anti-clique. Right, so far it just seems like we're improving Ramsey, but actually something stronger is true, which is that for any other B in the graph, there is some K, some uniform finite K, so that for any other vertex in the graph, either B connects to K, less than or equal to K, or to at most to all but K elements of A. Right, so here you are in your graph, you have this.
Yeah, but so A is a subset of G, and
A is a
we're
subset.
assuming that it's got this Ramsey property.
Oh, yes, did I say? Yes. So we have this huge graph and we have a huge set. So if you were just improving Ramsey's theorem, you might say you have a huge clique or anti-clique. But it's not just that it's a big clique or anti-clique, the way it interacts with the whole rest of the graph is different. Any other element, there's a uniform finite bound K, and now any other vertex in the graph either, connects to no more than 5 of the vertices or connects to all but 5 of the vertices. Okay, so the way that it sits inside the bigger graph is very deep than you would just expect by improving. Okay, so now so maybe I'll just say for a minute. Okay, so here we are in 1978. So now I want to say how this interacts with irregular pairs in Szemerédi's regularity lemma. Yes.
Can I ask what it means for R to be stable if there are some edges where we haven't specified whether or not they exist or not?
So in the graph, the edges or non-edges will always exist. So the only sense in which we haven't specified is when I give you a condition, like here's a condition, there is a half graph. So whether or not, I ask you, do there exist 4 vertices and 4 vertices with this pattern between them? And you can give me an example where it's a clique on the top and an anti-clique on the bottom or not. So I've left unspecified things in my structural conditions, but the actual graph itself will have edges or not. Okay, so something that happened between this and the introduction of regularity, which is now what I want to tell you about. So in 2009, in my thesis, I will say a little bit about this at the very end. There was a question of saturation of ultrapowers. So I proved some things about saturation of ultrapowers and how this connects to, certain locality conditions and so on. Regularity made an appearance, and of course, model theory. So right before the theorem I'm about to tell you, so there was this work that said these things can start to talk to each other. So this is why we're going in this direction. Okay. So now let's say something about Szemerédi regularity. Okay, so can I speak very quickly about the regularity lemma? No. All right.
I'm ready. No.
Okay, all right. I will speak at great length and slowly. Okay, so Szemerédi's regularity lemma is all right. So now we're in the world of finite combinatorics. It's a fundamental theorem. Tells you that huge finite graphs can be well approximated by small random graphs, which is obviously very useful. And when many people here have proved all sorts of interesting things about it. So let me just remind you. So theorem, Szemerédi, circa 1975 as part of his theorem proving that sets of positive upper density contain arbitrarily long arithmetic progressions. Okay, so for any epsilon greater than 0, I'll state a very simple version. There is a natural number and then epsilon, so that any sufficiently large finite graph can be equitably partitioned into no more, I'll say into L pieces, no more than N, so that almost all all but at most epsilon L squared pairs of pieces are epsilon regular. So what does epsilon regular mean? So here you are in your graph, you have two sets A and B, and you have the edges between them. So you can ask about the density, right? Number of edges divided by size of A times size of B. You can ask the question, if we take a small subset of each side, how much does the density change? And epsilon regular tells you it doesn't change very much. So the density between AB and A prime B prime differs by at most epsilon. Of course, we've forgotten something, because if we just take a single point, the density could be 1 if there's an edge, or 0 if there's an odd edge. So we have to say A and B are not too small. So if A prime subset of A prime has size at least epsilon times the size of A, and B prime subset of B prime has size at least epsilon times the size of B. Okay, and you could, as Szemerédi did initially, make these all different epsilons, but this is not our worry, right, in the bounds. So we'll make them all the same. All right, and equitably partitioned, so they initially all the pieces have exactly the same size. There's a small remainder that we distribute, so now they have size differing by most 1. Okay, so this is an amazing theorem. And notice that, of course, graphs are very complicated objects, so there should be some place where the complexity is hiding, and there are at least 2 places. So one is that the number of pieces has to be enormous as a function of epsilon. So this was proved by Gauss. Well, it was present already in Szemerédi's proof, and Gauss showed that this wasn't an artifact of the proof. In fact, it has to be true in general. Now, it's interesting that this isn't true for all classes of graphs. So Ron, Fisher, Newman, in the case of bipartite graphs, and also Lobachevsky and Szemerédi, proved that if you assume bounded BC dimension, you do get a much stronger regularity lemma, where the number of pieces is much smaller. It's polynomial in 1 over epsilon. Pieces which are regular, the pairs of pieces which are regular, have density close to 0 or 1. But it could be that they're still irregular pairs. So now we get to the other source of complexity. These are regular pairs. So there may be some pairs that don't exactly line up. Now, Szemerédi had found these irregular pairs in his original proof and had asked if they could be eliminated. And this was noticed by a number of people early on that no, there's a counterexample that shows you have to get irregular pairs. And the counterexample is a friend of ours. It's the half graph. Okay, so let's imagine that we have our A's and our B's, I's and J's. Okay, so irregular pairs have to exist due to the counterexample of half graphs. So let me give you a proof by example that irregular pairs show.
Irregular pair?
Irregular pair, it's so in your partition, Szemerédi's regularity lemma says it gives this partition of pieces. And the guarantee is that the pieces all have approximately the same size. And most pairs of pieces are epsilon regular, but not all. So you're irregular if you're not regular. And the lemma gives you, the statement of the lemma says some have to exist, but maybe that was an artifact of the proof, because you just, after all of these applications with Cauchy-Schwarz, could it be that there's a different proof that avoids irregular pairs? Okay, so let's see by example what the issue is. So if you have a huge half graph, it's Szemerédi's lemma is a theorem, so it will work here. But notice that, okay, so let's say I give a partition into the top and the bottom, and I have these edges going forward. So the density between this pair is about half. But if I take the first half and the last half, so that's a pretty big piece of vertices, and now the density is 1, right? So it's got from 1/2 to 1. In fact, if I take this piece and this piece, it goes to 0. So there's a huge fluctuation in the density on subsets that are not too small. So this is an example of irregularity. So now I have a partition into 4 pieces. Notice that actually I've made progress, because these 2 have density 1. So, so that will be regular on any subset. These 2 have density 0, but the ones across from each other have this fractal property where they stay irregular. So if you continue to partition like this, you will eventually get the number of irregular pairs down, because it's just the ones across from each other, which is a very quickly decreasing fraction of all pairs, but but they will remain. Okay, to actually prove this, you have to say that no matter how you try to give such a decomposition, decomposition, this would be true. Okay, so to my knowledge, so this had been a folklore example from a long time. For a long time, it hadn't been asked whether, this is the only place you get irregular pairs, for example. But if you look at this as a model theorist, as Shelah and I did, so this is our first paper in the context of a program on saturation of ultrapowers, and this is perhaps why we were looking in that direction. So if you look at this as a model theorist, you would say if irregular pairs are caused by half-graphs, then let's conjecture that they're the only reason, right? Because we have this nice stability and stability dichotomy. So perhaps if we had a bound on the size of half-graphs, we would get a much better regularity lemma that would, in which all pairs would be regular. And so this is true. So let me just tell you a little bit about the truth. Okay, so stable regularity lemma. So this is something, so 2011, 2014, so people started interacting with it when it was published. So if any, you try to write it in parallel, epsilon greater than 0 and natural number k, there is, so n depending on epsilon and k, so that any k sufficiently large, k edge stable graph has an equitable partition into, let's say L less than or equal to n pieces. All of them are regular, all pairs regular. And then, even though it's a completely different proof from the VC lemma, the other features look similar. So the number of pieces is polynomial and 1 over epsilon. And so all pairs have density near 0 to 1. But what's new is that each piece satisfies some kind of indivisibility condition. So this is why if you want to get all pairs regular, you want to make each piece look kind of like an atom, and then any two will interact regularly, essentially for free. So let me just say a few words about the proof. So what you
say something about the assumption, what does it mean? Sufficiently large K edge stable.
Great. Okay, so sufficiently large graph, and I'm inserting this as a hypothesis. So K edge stable means that there's no half graph, no bi-induced half graph of length bigger than K.
By induced?
Yes. I found now, so the difference is all of a sudden I've added the condition that there's a uniform bound on the size of a half graph.
And so we can think of it similarly to the dimension condition, but it's a slightly different.
Yes. So, and that's really one of the things that's interesting is that when you look from their finite point of view, how, what's special about it? VC is obviously interesting from the finite point of view, right? It's just, there's this clear difference between polynomial and exponential. It's clear something is going on. It's not really clear how much half-graphs are telling you, right? Why would you think of them as being special or having this special status? For that matter, irregular pairs. It's just this tiny thing that's not lining up. But maybe if your appreciation of half graphs is increased by your sense of what they do in the infinite world, you give them a chance, right? So what do we do? So let's prove this by trying to look for an analog of this theorem. So this theorem says you have linear sized.
So this theorem can't be proved directly with the finite world?
Oh, absolutely. I mean, the proof is completely combinatorial.
Right. So, but you have a much more general theorem of which this is an application of.
I'm going to prove a theorem in combinatorics, but I'm going to motivate it by looking at this. That's all. It was fortuitously here on the board above. And so, okay, so if we expect that graphs in the infinite world, stable graphs contain linear size sets, which have the property that any other element connects to almost all or almost none of it, then perhaps we can just try to find a finite version of this. So could you, all right, so here we are in our graph. So let's say A subset of G is epsilon good. Okay, here's just a very simple quantitative version of this. If any other element of the graph connects to all but, well, connects to or connects to all but epsilon times the size of A elements of A. So how might we try to find an epsilon good set? Well, here's our set. Is there an element which splits it into two pieces, both of size epsilon? If so, then put this as the root of our tree. Is there an element which splits this into two pieces, both of size at least epsilon? If so, but that is the root of the subtree. How about this? Okay, and if you continue too long, then you get a stability tree, which we've forbidden because we bounded the size by half graph. So in finally many steps, say epsilon to the d times the size of our original set, where d is the bound of the stability tree, you get this set that kind of looks like an atom, right? Nobody else slices off more than epsilon of its elements. Now, what you really want is something a little bit stronger than this. Any such set, any such epsilon good set, behaves kind of like an element. We can consider it a virtual element. Everybody else has basically either a virtual edge to it or a virtual non-edge to it, right? Because they connect to almost all or almost none of it. So what we really want is sets which have this property of being prime or atomic, not only for vertices, but also for virtual vertices. Okay, so you just have to do this twice, where the nodes of your tree are these virtual vertices, and then you can prove you get these indivisible sets, these excellent sets. And then what you've done is you've given a partition into these linear size sets that really look like atoms to every other vertex into each other. Then you have to make them all have the same size, which you can do randomly because you also have finite VC dimension, and then you have to partition the remainder. Okay, and so let me sum up. So okay, so a couple of things. So first of all, when you look at this picture, irregular pairs may seem like something very small, right? But as we know from Cantor's diagonalization argument, we never know how small something failing to line up really is. If you want to step back and think about where this is coming from, so let me say a few words about maybe a question that really is right. It's okay if I take a few minutes to summarize. Okay, all right. So just to say a few minutes about how this fits into a question that really interests me. So if you're thinking about this as a model theorist and you know classification theory exists and there's this beautiful theory of stability, you might ask the question, how do we find other dividing lines like that? You find stability because you happened maybe to count the right thing and there was a beautiful division, but there could be lots of other interesting partitions in the world like this. How do you find them? Do you just find them one by one? Is there a more open, a more systematic way of doing it? That's one question. And another question is, if you want to think about miniaturizing the structure theory of the infinite world to the finite, you have to look from the right point of view, right? So somehow all of these pictures were there hidden in plain sight, but how are you led to think about this? So for me, these really both had the same answer, and this was thinking about saturation of regular ultrapowers. So to say a few words, at the very core of all of these discussions is this notion of type, right? So a type in model theory, you take your model, you have a formula or you have a collection of formulas. So a type is a family of formulas that has the property that any finitely many of them have a solution in the model. Maximal consistent. So whenever you look at a structure as a model, you have all of these types associated to it, which are the things that are finitely approximated there. And those are the limit points. You have this natural notion of limit points associated to the structure, which doesn't really depend on a metric, only it's a very weak topology. And types are, of course, at the very center of what we've been doing so far, right? All of this stability was counting types, and also this was counting. Well, this wasn't counting types. Also, this was about types because this was saying that there's a set which generates a type, right? As a set which looks at any other formula and has a majority opinion. So you have these sort of special sets that generate types, their own average types within themselves. So you have these structures, you have these limit points associated to them, but as a result, you also have a way of asking about the completeness of any structure. Which of its limit points does it contain? So it turns out, if you want to ask fine structure questions about types and their complexity and where they come from, suggested by Keisler already in the 60s, maybe what you want to do is ask about completeness, not necessarily of any model, but of models that come as infinite averages of other models. Why is this a good tool for comparison? Because you're drawing the models from one class, you're drawing the models from another class, your averaging mechanism is the same. And then you ask the question, are there limit points? Is this complete? Is this complete? And that starts to give you a mechanism for comparing theories, comparing elementary classes. So this is something that sees stability, but allows you to see more. The C stability was a theorem also from classification theory, but also was sort of what was behind these initial connections to regularity, which I may say more about later. Okay, thank you. Okay.
Takes more questions. We are a bit late, but please.
Yes, I was curious. So this finite lemma is sort of theorem is what was used to prove something about cardinality?
Okay. So I guess there are two directions. So this you can see the theorem about infinite cardinals is saying something about this theorem. So what I wanted to say, connecting it to Keisler's order, was that so Keisler's order is this question about saturation of ultrapowers, which will also play a role in the set theory talk on Wednesday. And when you look at Keisler's order, you think it might really be something set theoretic. Maybe it doesn't have to do with model theory at all. It's just these very complicated questions about cardinals and ultrafilters. So when I was thinking about this in my thesis, something I had proved about Keisler's order that was just, to me, the thing you would prove if you really wanted to try and understand if it was model theoretic was that it's local. So the same way stability is, something you can count about theories, but is really about the slices, about the types. Also, Keisler's order is local. It's about these slices. And so that means that you're not getting this interference from somehow complicated things, all the formulas working together. It's really piecewise. You're looking at these, these families of all of the same formula, a bunch of intervals, a bunch of polynomials, whatever. And that's what's that's what's giving you the picture of complexity in Keisler's order. So at that point, you try to start analyzing it, and you can see that there's some family of finite graphs, maybe growing finite graphs and hypergraphs that are controlling the incident structure of what's going on. I was calling this the characteristic sequence. And then I could show that for an important class of theories, which were not in any way stable, these graphs associated to them that was controlling the structure were stable. So this is why you want to look at, this gives a model theoretic motivation for studying large finite stable graphs. And so I had, given some preliminary theorems saying that maybe Szemerédi regularity applied to the sequences can tell you things in model theory, right? But this was just, just sort of getting things to talk to each other. This you can see is, model theory talking to regularity in the other direction. I do think there's much more to say, but but you really want to build a bridge that says something surprising. So there will to be continued. Okay.
So one of the advantages of having a series of 3 lectures is that the lecturer is here for the whole week, and you're in full toll, and you can follow up on all questions and get all your answers, not necessarily in the lecture, but in between the lectures.
I don't promise all answers. Many answers.
So let's thank Maryanthe.